come to an important concept about sequential circuits, which is the characteristic table. So like I mentioned, there are three types of tables we will be using in this chapter: the function table, characteristic table, and the excitation table. Mostly in terms of, if you look at the columns they have and the type of values they take, they might sound slightly similar, but they have different purposes. We'll see. So the function table we already saw. It explores the different input combinations and what the next state would be. And it defines the next state generally in terms of zeros and ones. The characteristic table again takes the input combinations and gives you the next state in terms of the previous state. So we will look at this and understand. So SR flip-flop, if you take 0, 0, t here refers to time, by the way. So q of t means the current state at time t, and q of t plus 1 means the state at time t plus 1, which is this next state. So in an SR flip-flop, if your S and R are both 0, 0, then your next state is going to be same as your current state. Q of t plus 1 is equal to q of t. If S and R are 0, 1 respectively, then irrespective of what your current state was, this is what your next state is going to be. Q is 0. Similarly for 1, 0, 1, 1, and the same analogy continues for all these. So instinctively this looks very similar to the function table, except that instead of using q of t plus 1, we just use zeros and ones there. So if it was the same as the previous state, we just looked at what the previous state was and copied that down. Here instead of that, we are writing q of t plus 1. So both might look similar, but there is not much of a difference, a very subtle difference. The idea is the function table just tells you how the flip-flop or the latch works. So when I give these inputs, it gives me this output. So for instance, if you take this is the function table. Here again, you also in these function tables, you can change the sequence in which you give the input. So this is 0, 0, 0, 1, 1, 0, 1, 1. Instead, if you give these inputs in a different sequence, 0, 0, 1, 1, 0, 1, 1, 0 also, they will still give the corresponding outputs. That is a miscellaneous point I meant to add, by the way. So coming back to our discussion about function table versus characteristic table, function table helps you to understand the working of the flip-flop or the latch. Now the characteristic table is just a more generalized version of a function table, where instead of copying the previous state, you just mention q of t for the previous state, and similarly. And so what does the characteristic table help you find out is, given these inputs and given my current state, what would my next state be? So this is an important point. The key to understanding the difference between the characteristic table and the excitation table, which are the two tables we will frequently be using, is to identify what insights can be gained from each table. So what insight can you gain from a characteristic table? Given this set of inputs and given this is my current state, what will my next state be? That is what the characteristic table tells you, and that is what the function table also tells you. So there is not too much of a difference between a function table and a characteristic table. So in fact, the only tangible difference is there you just copy the previous state, as I said. Here you express it in terms of q of t and t plus 1. Now we will look at the excitation table, but before that we see this characteristic equation, which is just a function or an expression for the next state in terms of the input and the current state. How do we get this? From the characteristic table. So you take S, R and q of t as the inputs. Again, q of t can be a 0 or 1. So you have S, R, q, which are three variables, three inputs. You draw a k-map and you fill in the zeros and ones as specified here. You do the grouping, you will get an expression for your q of t plus 1, which will be this. Similarly for j, k, d and t. So if you have this equation, given these values and given your current state, you can find out your next state. So, and how do you get this equation? From the characteristic table. So that is what I was telling you. Given some inputs and given a specific current state, what is my next state? That is what the characteristic table helps me find, and that is what the characteristic equation also helps me find, because the equation is effectively derived from the table. Now moving on to the excitation table, it also has the same values, state, next state and flip-flop inputs, but the difference being, what insight can I gain from an excitation table? Given this is the current state and given this is the next state I want to move to, what should my flip-flop inputs be? So it is sort of the converse of what you would get from a characteristic table. So if you are in a situation where you know the inputs and the current state and you want to know the next state, you have to employ the characteristic table or equation. And if you are in a situation where you know the current state and the next state but you don't know what inputs to give, you have to use the excitation table. So the columns as such are the same, current state, next state and inputs, but what you want to find out is the difference. And this again is also derived from the function table only. So if I am currently in 0 and I want to go to 0, I have to give a 0 0 input and so on and so forth. So you will notice that this ties in with your characteristic table and with your function table. If you sit and draw all of them side by side, you will notice that they are, what to say, they all tie in together, so there is no inconsistency between them. The idea of which table to use where depends on what I want to gain from or what kind of information am I looking for. So to quickly recap, function table and characteristic table are very similar. They give you the inputs and given the inputs and current state, they tell you what the next state is going to be. And by drawing K maps using the inputs and current state, if you get an expression for the next state from the characteristic table, it's called the characteristic equation. That also helps you find the same thing. Now given the current state and knowing what my goal state or destination state is, if I want to choose my inputs accordingly, I use the excitation table. And that is why this one is used in your counters and all, because in a counter, you know your current state is a 0, you want to move to a 0 0 1, but you don't know what inputs to give, so you use an excitation table and so on and so forth.